All right, let's go ahead and take a look at checkpoint 14. So getting back into calculus. I assume most of you took Math 213 recently. So you probably did and when you're doing brief calculus, you did single variable functions. So basically what we're going to do for when you were doing derivatives, we're going to jump back into derivatives. But now instead of doing single variable functions, we're going to scale that up to functions that have multiple independent variables. So this first question here, we're not going to be doing any derivatives with it, but we are going to be graphing. So I have this function of two independent variables, x and y, and want to graph it by basically got a lot of steps here. And what these steps are going to help us do is to graph this kind of methodically. So first I want to graph slices of this. So first thing I'm going to do is draw myself a coordinate plane, or not plane anymore. Coordinate system, which has three variables. And one thing I want to impress on this, and basically the thing I'm asking you to do is inherently, I am by default asking you to do basically to use the wrong tool for the job. And what I mean by that is I am asking you to graph on a two-dimensional surface or a flat piece of paper. I'm asking you to graph a three-dimensional thing. So because of that, it's gonna be hard, it's gonna be bad. And I say that not to kind of like set you up for failure. I say that to liberate you. My goal for you is not for you to draw pretty or beautiful graphs. My goal for you is to just get a sense of comfort and to get an idea of how this new coordinate system works. That's all I want. So it's much more important to me that that you feel confident about how to use this coordinate system than you are able to draw like really stunning graphs. As you will see, I do not know how to draw great graphs, but I know my way around this coordinate system, and that's really all you can ask for. So when we say we're graphing slices, basically what we're doing is this. I assume by now many of you are uh, more comfortable with graphing single variable functions than you are with graphing functions that have multiple independent variables. So what slices allow us to do are to basically take one of our variables, make it constant, and graph the other two variables in response. So basically, what I'm going to do is this. For part A, I'm reducing my function to this. So I'm going to rewrite f of x and y as z. So z equals 25 minus -3 squared minus y squared. So that's 25 minus 9 minus y squared. So that's equal to 16 minus y squared. So z equals 16 minus y squared. Do I know what z equals 16 minus y squared it looks like? So I know what things of this form look like. That looks like a parabola that opens downwards. So it opens kind of like this. But what variables does it unite? So that unites the z and the y variables. So as y changes, so y is like this left and right variable, and z is my up and down variable. So even though these are in y and z, they're kind of like how we think about x and y changing together. So I have a parabola. One thing we do need to pay attention here is that this is when x equals -3. So what I'm going to do here is I'm going to go backwards. -1, -2, -3. So when x is -3, I have this parabola 16 minus y squared. So basically, when x equals -3, when y equals 0, I'm going to have a z value of 16. And as y deviates from 0, you're going to have this fall off. Basically, this is going to be like the vertex of the parabola. And as I go left or right, this parabola is going to fall off like this. So that's one slice of this surface. So, and that's another big difference here is that when you're graphing a single variable function, you get a curve. When you're graphing a multivariable function, you're graphing a whole bunch of curves. And when you stitch those curves together, you get like a surface. So when we finish this, we're going to wind up with a surface. So let's graph another slice here. So this was the slice when x equals -3. So let's do another one. Now when x equals 0, we're going to get z equals 25 minus 0 squared minus y squared. So when x equals 0, we're going to have 25 minus y squared. So that's going to be a parabola of basically, a very similar shape, but it's going to extend higher up on the z-axis. But it's going to be like more into the foreground because it's not going to basically think about the x-axis as extending. The positive x-axis comes out of the page and the negative x-axis goes into the page. So basically that when x equals -3, that curve that I drew is like sunken back 3 places backwards into the page. So then what I'm looking at here is I'm going to draw this graph's going to be a little higher up and forward. All right, and then finally, I think this next one, if I plug in 3 for x, I'm going to have z equals 16 minus y squared again. So that's identical to the first slice that I drew, except now this is going to be 3 units into the foreground. So I'm going to draw that graph into the foreground, vertex about there, something like that. So those are my slices in the where I have my x values constant. So I'm done with step A. Now I'm going to use now I'm going to graph slices with y values held constant. So I'll do my scratch work up here. So z equals 25 minus x squared minus, and we're going to set y equal to -3 squared. So z equals, stop connecting those, 25 minus x squared minus 9. So z equals 16 minus x squared. All right, so now we have a slice that's uniting z with x. And now we're fixing y to be a constant -3. So y is the horizontal axis. So now I'm going to go backwards in the y-axis, which in this case is left. So y, -1, -2, -3. So when y is equal to -3, let's let x be equal to 0. What does x equal to 0 mean? That means that I'm not going to go in or out. That means I'm going to just be basically on the page, not behind it or in front of it. And then where is z going to be? That's going to be this parabola here. But now, if I deviate from that vertex of that parabola, so if I go away from that vertex in the x direction, what does that look like? Well, what that looks like is that basically I'm going to be deviating in the x direction. So I need to be parallel to the x-axis, so that's going to kind of look like this. And like, here's the thing, I'm going to admit to you, I don't think that looks very good. but I know what I'm supposed to be doing. I really wanted that to be parallel to this x-axis, but I'm going to just impress upon you again. I'm not trying to make I'm trying to make it look as good as I can, but that's not really the end all be all goal here. The more important goal here is to get as comfortable as you can with this coordinate system. All right, so that's one slice in the y direction, or fixing the y value. Now what happens when y equals 0? We're going to get z equals 25 minus x squared. So we should get some very similar looking equations that we got from part A. So 25 minus x squared. So that's when y equals 0. So this is going to be over the origin again. But now we're going to get a curve that basically we're going to get a curve that's like, it's going to meet this other one, but it's going to be perpendicular to it. And then finally, we're going to get another z equals 16 minus x squared when y equals 3. And that one's going to be parallel to the first slice we drew. All right, so I got a bunch of slices there. They're all kind of like, got this dome pattern that's kind of appearing. So we got all of our slices for B. Now C, we have level curves. So basically, for A and B, we had slices, or I think the videos probably also used the term traces. Basically, we had traces where we held X constant, traces where we held Y constant. Level curves are basically what happens when you hold the dependent variable constant. So let's do my scratch work for that. I'll try to squeeze it in here, see what happens. So now we're going to hold Z constant. So 9 equals 25 minus x squared minus y squared. So that's negative 16 equals negative x squared minus y squared. Everything's negative, so I can make everything positive. X squared plus y squared equals 16. You may recognize that as a circle. X squared plus y squared equals 16. So that is a circle of radius 4. So it's a circle of radius 4, but where is that circle going to be? Well, that's a z value of 9. So remember that the highest these curves got was 25. So I'm going to have a circle of radius 4. Let's put it about here. And I'm being really rough with this, but that's okay. And then 16. So if I set up another one like that, I think by symmetry, that's going to be x squared plus y squared. Terrible. X squared plus y squared equals 9. So when z is equal to 16, okay, yeah, when z is equal to 16, I should have circle of radius 3. So I think this needs to be a little larger. Okay, this one makes more sense. And then finally 21. This last one is going to be x squared plus y squared equals 4. So when z is equal to 21, I'm going to have a radius of the square root of 4. That'll be 2. So something like that. So not totally to scale, but like I said, we're just looking for a sketch here. So part D, I've been basically doing this all together. So I got kind of an idea for a surface here. Basically, this is what's called a paraboloid. Basically, if you were to take a parabola, which by now you've seen lots of those, and basically rotate it in all directions, basically rotate it around its vertex. That's essentially what a paraboloid is. All right, part E, explain why the domain of F is all values of x and y. Lots of ways to explain this, but one way that you can explain it is basically this. When you think about domain, you can think about what values of X and Y can you use that are going to fail to deliver an output. And in this case, what are you doing with X and Y? You're squaring X and Y. Are there any values of X and Y that you can't square? No, there aren't. Okay, so after you square them, are there any values of X and Y that you can't subtract from 25 or subtract from each other? No, there are not. So because of that, because there are no values that are going to make this undefined, every single value of X and Y, basically any combination of X and Y, are going to be in this domain. And finally, the range of F is all values of Z such that Z is less than or equal to K. So basically, I'm telling you the range of F has a maximum. So the graph, if maybe the graph you drew by hand helped you, or maybe you graphed this by Desmos or some other technology. But basically, a parabola or a paraboloid has a vertex. It either has a maximum or a minimum. In this case, it has a maximum of 25. You can also maybe get a sense of that by looking at this definition. 25 minus x squared minus y squared. X squared can never be negative. It's going to be 0 or it's going to be positive. Y squared, same thing. So you got 25 and you're subtracting these two values that have to be at least 0. So because of that, this value of K is 25. All right, that's all for question 1. Question 2. Store manufactures bicycles and tricycles. Its weekly cost for producing them, X bicycles and Y tricycles, is given by C, and I give you this function here. So now we're going to do a little bit of calculus. So part A is to find partial, let's just do them one at a time. This thing, so the partial derivative of C with respect to X. So basically what I'm going to do here is find, in a lot of ways, this is no different from the way you found derivatives in 213. One thing I'm going to do here is this. I'm going to rewrite this function in a way that makes it easier to think about using the power rule, which is probably the first way you talked about finding derivatives in your brief calculus class. So I'm going to say 50x to the 1/2 times y to the 1/2. Okay, so basically I'm going to run through this term by term. And basically the only variable I'm looking for is x. So 20,000 is a constant. The derivative of any constant is 0. 60x, the derivative of 60x is 60. 20y. Y is a variable, but I'm taking a derivative with respect to x. So as far as that derivative is concerned, 20 is a constant. Or 20y is a constant. So that's going to vanish. Okay, so next, 50x to the 1/2. Okay, so x to the 1/2, that's going to be a variable. So I'm going to use the power rule. So plus 1/2 times 50 times x to what power? I take the 1/2 and I subtract it by 1. So that's x to the negative 1/2. And then the y to the 1/2, I just keep that. Basically, if it's an added constant, those derivatives are 0. If it's a multiplied constant, I basically carry those with me. Kind of like this 60x. The derivative of x is 1. But that 60 was multiplied by it, so I just take that 60 with me. So that's a good partial derivative for C with respect to x. But now I want to do partial C with respect to y. So let's just run through it again. 20,000 is a constant with respect to y as well. 60x is a constant with respect to y. 20y, the derivative of that with respect to y is 20. Let's do this. Let's clean this up a little bit. This is going to become 60 Let's not try to squeeze it on that line. $60 plus 25 square root of y over x. All right, now let's do this partial. And we said 20 plus 1/2 again, but this time it's the x that's the constant. So 1/2 times 50, and this time it'll be x to the positive 1/2 because that gets left unchanged, and the y is the one whose power gets reduced by 1. And this one we can rewrite to be 20 plus 25 times the square root of x over y. So those are my good partials for A. All right, now part B is to find more partials, but they're second order partials. So how do I find second order partials? Basically, well, let's just go through it. So one thing I want to point out here is that this thing, I can also call it C sub x. I can also call this C sub y. So if I want to find C sub x, that is the same thing as me taking the partial with respect to x of this partial, cx. So let's go ahead and do that. The derivative of 60 with respect to x is 0. And this other term, I can use power rule it in again. So all the constant stuff I can kind of just take off to the side. So 25 y to the 1/2 times negative 1/2 x to the negative 3/2. And if I simplify all that stuff, what do I get? I get negative 25 over 2. And let's just keep all the exponents the way they are. Times y to the 1/2 over x to the 3/2. All right, so that's cxx. How about cyy? Same kind of scheme there. So cyy, the 20 vanishes because that's a constant. And the rest of this is going to be, so that'll be 25 x to the 1/2 because as far as y is concerned, that's all constant. And then if I take a derivative of the y term, it becomes negative 1/2 y to the negative 3/2. All right, so if we keep simplifying, we get same coefficient, negative 25 over 2. Actually, this should look awfully similar, just with the terms flipped. So x to the 1/2 over y to the 3/2. All right, and then the rest of these. So now we have c sub xy. So what does that mean? That means I take this partial derivative with respect to x, and I take that derivative with respect to y. Okay, so what's the derivative of the 60 with respect to y? That's still 0. And then what's the derivative of this next term? Essentially 20x to the negative 1/2 times y to the 1/2 with respect to y. So that'll be, first, let's do the same thing. Let's bring all the stuff out that's a constant with respect to y. So that'll be 25x to the negative 1/2. Now what's the derivative of y to the 1/2? That'll be 1/2 y to the negative 1/2. So what do we have now? We have positive 25 over 2 times, and I think that's all over x to the 1/2, y to the 1/2. And finally, what is c sub yx? I am not sure if this came up in the videos. I didn't see it, but one thing I'll tell you now is that these partials, these mixed partials, I can't remember what the condition is, but it's I will tell you this, in all the functions we're going to handle in this class, these mixed partials will be identical. So I can tell you that no matter what the order is, including this case here, these mixed partials are going to be the same. So those are the second order partial derivatives. Excuse me. All right, so that's it for A and B. All right. Do I have enough room to do C and D? I really don't want to erase anything because I need a lot of information. Okay, so we'll get there. Okay, so what does part C ask for? Part C, how much does it cost to produce 625 bicycles and 121 tricycles? Okay, so I just started messing with this function because it just asked for derivatives. Didn't even really look at what this function says. So a store manufactures and sells bicycles and tricycles. Its weekly cost in dollars of producing X bicycles and Y tricycles is given by C. Okay. So how much does it cost to produce them? Okay, so basically what this is asking for is to evaluate the function at X equals 625 and Y equals 121. So what is 20,000 plus 60 times 625 plus 20 times 121 plus 50 times the square root of 625 times 121. And stay tuned. All right, so I got $73,670. So that's how much it costs to produce. That's the total cost to produce all these bicycles and tricycles. So I'm gonna go ahead and erase that because I don't think I need the answer to C to get part D. So I'm gonna save myself some space. All right, so part D, what is part D asking? What's the marginal cost of producing one more bicycle and one more tricycle? Okay, so I really think I need two different values here. So what's the marginal cost? How do I find the marginal cost? So the marginal cost comes from the first derivative. So what's the marginal cost of producing one more bicycle? So that is going to come from, so the marginal cost of producing one more bicycle, that's going to be C sub X. But at what conditions? That's going to be 625, 121. And we already found that derivative. We said it was 60 plus 25 times the square root of Y over X. So 121 over 625. So that's equal to, stay tuned. So it'll approximately cost $71. Or I got that exactly. It'll cost, well, the marginal costs are approximate. It'll cost approximately $71 to make the next bicycle. What about the next tricycle? So the marginal cost of the next tricycle at these levels will be 20 plus 25 times the square root of x over y. So 625 over 121. So marginal cost here is, I felt like that should have come out to an integer. Let me try it again. 625 over 121. Nope, got the same thing. This comes out to be 76.82. So it cost approximately $76.82 to produce the next tricycle at these levels. All right, so that's all for checkpoint 14.